Well, greetings, mathletes, and welcome back. Um, so, today's lecture, we're going to start talking about trig functions. Now, these are the whole point of the semester, right? These six functions is what makes this class a trig class. And any class that you're studying and using this function is considered a class you're using trigonometry. So, without any further delay here, let's go ahead and get started. So there are six trig functions that we need to be dealing with, right? And they all have to do with sides of a triangle. Now, I'm not going to use a conventional mathematical labeling here because I think it actually gets in the way. Normally you'd give these letter designations, but I actually want to give them names. So here I'm going to pick that to be the angle that I'm dealing with. I'm going to call this angle theta, right? And so theta is a Greek letter. It looks like an O with a line across the middle of it. And that's one of the Greek letters that we'll be using. That's the Greek letter theta. Some of the other ones we'll use that are pretty common. That's alpha. That's beta. In fact, that's where the word alphabet comes from. Alpha, beta. It's like saying ABCs, but in Greek. Let's see here. What else do we see? We see gamma. Yeah, those are probably good ones to get us started. But in any case, the angles are typically denoted with a Greek letter. And then these sides here, the side that the angle doesn't touch, right? So the sides of the angle are here. The side that isn't a side of the angle is called the opposite side. This side here, excuse me, the long side of this it's just the hypotenuse. It's a right triangle. That's the hypotenuse. I'm going to run out of room. That's the hypotenuse. And then this side here is the other side. Now, the hypotenuse is adjacent to the angle. The other side that is touching the angle is called the adjacent side, right? So there's two sides that are adjacent to an angle. One is the hypotenuse. The other side we just call the adjacent side. Okay, so these three sides are going to determine the values of the function when we put in an angle. So the first trig function is the sine function, right? That's how it's spelled. The abbreviation is sin, right? So you'd put sine and then the angle that you're taking the sine of. Now, this is a function. This is not sine times an angle. This is sine of an angle, the same way you take f of x. The sine is determined as the opposite over the hypotenuse, right? So it's a ratio. Just so we understand what we're talking about here, let's see here. I know if I have a 30-degree angle here, this side is 1 and this side is 2. That's just something I happen to know. We'll see why here in a little bit. So what that means is if I take the sine of 30 degrees, it's the opposite side, 1, over the hypotenuse, which is 2, so the sine of 30 is 1/2. So you can actually pick these things out of the triangle. Now, I've only talked about one function here, but I kind of wanted to show you what it did before I put any more on here. Let's see here. So let's go ahead and get rid of that. Hey, come on now. That's a very accurate eraser. Okay. Now, there is also, so we started with sine. Now we have cosine. Cosine is the adjacent divided by the hypotenuse. And then tangent, these are your big three, sine, cosine, and tangent. Tangent of theta is actually, it's going to feel a lot like computing a slope, because it really kind of is, right? The opposite side here is a rise, and the adjacent side is a run. So we really are talking about a slope here. So tangent theta is the opposite over the adjacent side, right? So it's this over this. And if you're actually looking at this being like the equation of a line or something like that, right? You could look at this as your change in y and this as your change in x. So these things do tie into the regular algebra quite a bit. In fact, we end up using that. And those of you going on into calculus, this becomes extremely important. Okay, so we have these three here. Now, I'm going to stop here with just these three, and then I'll talk about how to attach the other three here in a second. But there's a way to remember which ratio goes with which. And I've seen it several different ways, but I think this is probably the best acronym. Is this idea of SOHCAHTOA, right? And what this means is S is for sine, right? Sine is the opposite over the hypotenuse, right? So you can actually use the first letter of each one. This is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And tangent, I'm spelling these downwards, by the way, is the opposite over the adjacent. Right? So you can actually use this SOHCAHTOA to remember what goes with what. Okay. Yeah, so the SOHCAHTOA thing is actually quite useful. I still think about it sometimes when I'm looking at trying to figure out which trig function I'm going to be using for something. Quite often I'm still referencing that in my head. Okay, so let's go ahead and clear this out. There it is. Let's go ahead and do this. I'm going to get rid of these guys. And there we go. All right, so let's get back to this. Now, let's kind of take a look at how this is used. One of the things, and I'm just going to show you a quick use, and then I'll show you some of the exercises we're going to be doing here. I don't know, let's say I just have a tree here, right? Oh, I probably don't need to draw this like a nice tree. Actually, it looks better that I scribbled it. Okay, so this is Mr. Bryan's tree. Quite a gardener. And you're just trying to figure out just how tall this thing is, right? So you take some measurements. You can figure out how far you are from the base, right? And so you measure out a distance from the base of 35 feet, right? Then from that point, you measure this angle. This is called an angle of elevation. It's how far you have to turn the angle upwards to find something. Okay, so we measure this angle, and we find that this angle is 40 degrees. Okay, so this is actually where we end up using our calculator for this stuff. But one of the things you should be able to see here is that there is a right triangle hidden in this whole thing, right? I can actually make a right triangle here, and with this tree at the right angle. Now let's look at what we have here. I have an angle, I have 40, and I'm looking for a height, so this is what I don't know, and I'm given another distance here. Right, so we have one side and an angle of a right triangle. So technically we have two angles because we know one of them's a right angle. But Let's look at this here. So the two sides we either know or are interested in are the opposite side, right? This is the opposite side, and this is the adjacent side. And so I asked myself, what things relate? Which of the trig functions relate an angle to the opposite and adjacent side? And if I look over here, I can see that it's tangent. So what that means is if I want to compute this, tangent of theta is equal to the opposite over the adjacent. Well, 40 is my theta. So if tangent theta is the opposite over the adjacent side, then that means that tangent 40 degrees, is equal to the opposite side, we're calling that x, over 35 feet. Right? And that's tangent 40 is just going to be a number. Right? That's something that you end up plugging into your calculator. In fact, we'll talk about that here in a second. So what I really want to do here is just solve for x. And since this is a fraction, if I multiply both sides by 35, I'll get rid of this denominator, and I end up with 35 tangent 40 degrees is equal to x. Now, I need to make sure, and you need to make sure actually, that you can put this into your calculator and get the correct answer. So the first thing you want to do is make sure that your calculator is set to degrees. Since our angles are in degrees, they're not in radians, we have to have our calculator set to degrees to be able to do this. So there should be a setting in there. Sometimes it's a second function, sometimes it's a button that says mode. If you have a calculator that's not a graphing calculator, there's probably a button somewhere that says degree radian. It'll say deg, DEG, RAD, and GRAD. So you want to make sure that is on degrees, the DEG. If you're having any issues with finding this stuff on your calculators, it's definitely a good thing to come see me about. I have an older calculator, but I can still help you with yours. Nonetheless, here's how you can check now to see if you did this correctly. What you should get is something around 29.37 feet is equal to x. So it's about a 30-foot tall tree, right? Decent sized tree, right? And that was by just computing this. So one of the things I want you to remember, if you have a trig function, right, t of x, oftentimes in pre-calculus and trig books, if you're talking about a trig function in general, but not a specific one, you use a capital T. This trig function, basically what it does is it takes an angle and it maps it to a ratio. Right? So the input into this thing is an angle. The output from this thing is the side ratios. So that's what you want to be remembering. Trig functions, you stick in an angle, what you get out is a side ratio. Okay, so let's go ahead and get rid of this. Take a look at another one here. And I want to talk about the other three trig functions. Now, the other three trig functions are basically reciprocals of the first three. They are, let's see, the reciprocal of sine is cosecant. Oh, this always works better with the, there we go. Let's try this again. Okay. Cosecant is abbreviated this way. It's spelled, I'll spell it over here. Cosecant, right, is CSC. Is equal to the hypotenuse over the opposite side The reciprocal of cosine is secant, which would be the hypotenuse over the adjacent side. And then the last one is cotangent. Oh, I almost wrote the whole thing out. Hang on. Cotangent theta, which is the adjacent over the opposite. Now, there's some other nice things that happen also. Because of this, cosecant can also just be looked at as 1 over sine theta, right? It's what we call an identity. And I don't know, you may or may not have covered it in algebra, but one of the things that we call an equation that is always true when the solutions are all real numbers is that equation is an identity, right? It doesn't matter what you put into it, it's always true. So it doesn't matter the angle, cosecant theta is always the reciprocal of sine theta. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. And what ends up happening is these become substitutions we can make. And there's one more that we're going to be using also, having to do with tangent. But it turns out that when you're manipulating these things, and we will be manipulating them algebraically, just not today, not so much today. One of the things that's often very, very useful is to take everything and rewrite it in terms of sine and cosine. So, right, if I have a cosecant, I'd rather write it as a 1 over sine. If I have a secant, I write it over as 1 over cosine. So now I can turn all my secants and cosecants into sines and cosines. And then there's one more. The other identity that I haven't talked about here, it's probably a little less obvious, is that tangent theta is sine theta divided by cosine theta, right? And that actually happens if you take this. Let me switch colors. If I take these definitions of sine and cosine and I just write sine over cosine, when you flip and multiply, the part of it cancels out and it just comes back down to sine and cosine again. So, or yeah, and it comes back down to tangent actually. And if this is true, that also means that cotangent is cosine over sine, right? So we have this is a whole bunch of stuff. So I'm hoping you're writing this stuff down. These are going to be the bread and butter for pretty much most of the semester. Even in the last chapters of this, we will still be using these definitions and identities, and they definitely help. What is most useful really is that these trig functions relate an angle, the change in an angle, to a height or a distance, right? It doesn't have to be a height, but it relates it to a distance. So if you have something you're working on where you have a connection between an angle and a distance, it's probably one of these functions that's connecting them. And it's just a matter of figuring out which one and how it's being used. Okay, so let's go ahead and clear this off here. Let's see, let's go back to that. Let's just do this. Okay, so here's one of the types of exercises you may see. Say, do I have? Yeah, I'm good. Okay, so let's say I have a triangle. It's a right triangle. And I know a couple of sides of this triangle. I know this side is 5. This side is 2. I don't know what the angle actually is, so I'm just going to call it alpha. So this is angle alpha. I know sometimes to some of my students this has been called angle fish. I see it, but I don't know. Alpha sounds better to me. Okay, so here's the task that we're supposed to accomplish here. We want to find the value of all 6 trig functions. of alpha. Okay, so they're saying that this is in reference to the angle alpha, so that means all of our side ratios are going to be decided by where alpha is. So that means that this is my opposite side, this is my adjacent side, and this is my hypotenuse. Right? And so I can piece together all the ratios that way. But we do have one problem. We're missing a side. But we're in luck. This is a right triangle, which means the Pythagorean theorem is very much on the table. And actually, interesting little fact, in The Wizard of Oz, when the Scarecrow got his brain, the first thing he did was recite the Pythagorean theorem wrong. I thought that was pretty funny. What he said was, he said the sum of the squares of the legs of an isosceles triangle is equal to the square of the remaining side. And he said isosceles triangle, and it should have been right triangle. So the sum of the squares of the legs, right? The legs are these size. So the sum of the squares of the legs, so that means if you square them and add them up, it's equal to the square of the remaining side, right? But that's only true for right triangles. And that's that whole a squared plus b squared equals c squared. I actually don't like that phrasing of the theorem, because most of the time people completely forget about the fact there's a triangle involved with it. But what that means is that I'm just going to give this side a name. I don't know. I'll call it y. Why not? Let's see here. We need to find what y is equal to. So that means that 2 squared plus y squared is equal to 5 squared. Right? Just using the Pythagorean theorem. So 4 plus y squared is equal to 25. And if I subtract the 4, y squared is equal to 21. And what that means is that y is equal to the square root of 21. So now I have a side. Okay, now if I'm going to write all this stuff down, I'm going to need a little bit more room. So I'm going to erase part of this. I'm going to get this out of here. That's our little Pythagorean computation I'm erasing here. Okay, so we have that that's the square root of 21. So now we just need to put the ratios together. So we got sine alpha, cosine alpha, tangent alpha, and then cosecant alpha, secant alpha, and cotangent alpha. And they're all, the last three are reciprocals of the first three. Yeah, so sine alpha is the opposite over the adjacent side. So this would be the square root of 21 over 2. That's it. We just write it down once we find it. Cosine alpha is the adjacent over the hypotenuse. Oh, I just wrote sine wrong. Let's try that again. So sine alpha is the opposite over the hypotenuse. I don't know why I wrote 2. It's over 5. Cosine is the adjacent over the hypotenuse, so it's just 2/5. Tangent is the opposite over the adjacent, so this one is the square root of 21 over 2. And then we have our last three here, and I actually want to put a little more room between these because I'm already running out of room. Okay, so we had cosecant alpha, secant alpha, and cotangent alpha. Now these guys are all reciprocals of the first three. Cosecant's the reciprocal of sine, and so you could do hypotenuse over opposite in your head if you wanted to, but we already have sine. It's just going to be 5 over the square root of 21. Now, this is part of the reason we did radical review at the beginning, was because of the fact that we have square roots in the denominators here. So I have 5 over the square root of 21 there. This is going to depend on what book you're using. With the advent of calculators and the fact that we can get a decimal approximation easily without having to do anything by hand, it's actually not a big deal to leave the root in the denominator. However, a lot of places still expect you to rationalize the denominator. So that's what we're going to do, just so we know here. I can't leave that root in the bottom. This book is going to insist that you rationalize the denominator. So we have to multiply by square root of 21 on top and bottom. And that's going to give us 5 root 21. I'm running out of room. Ooh, let's drop down. Over 21. And that doesn't simplify. So we have 5 root 21 over 21 is what we would actually write as our final answer there. Secant is the reciprocal of cosine, so that one's not bad. And then cotangent is the reciprocal of tangent. So now we have 2 over 21. I'll do this one over here. Square root of 21, excuse me. If I multiply by root 21 on top and bottom, I get 2 root 21 over 21, and nothing reduces, so we're good. So this is 2 root 21 over 21. So these take a little bit of work, but let's walk back through what we just did, because I tend to ramble, and I know sometimes my ramblings get distracting. We needed to find the 6 trig functions for this angle. We don't know the angle, right? You don't have to know the angle to know the function values. All you need are the triangle sides. So we were missing a side, so we used the Pythagorean theorem to figure out that this missing side was equal to the square root of 21. Then, once we had all 3 sides, we could set up all of our side ratios one at a time, right? So we have all 6 of them, and all 6 of their values as well. So I got that value, that one, this one, this one, and this one, right? So this is one of the tasks that you're going to need to be doing. All right, so I want to play a little bit more here. So let's go ahead and get this off of here. Okay, so this one I want you guys to try it out and just see if you can walk through the whole process of finding all 6 trig functions from this triangle. So let's make sure, let's see, let's turn that back on. Let's try this again. Okay, let me reorganize here. There. Okay, so here's our triangle. And the measurements we have are 6, square root of 5, and this angle we'll call beta, right? So that's the angle beta here. And we want to find all 6 trig function values. For beta, right? That's what we're going to be working on. Okay, so go ahead and pause here and see if you can scratch it out. Go ahead and pause it. I said pause. Okay, so let's go ahead and take a look at this thing. So we have a missing side, right? I'm going to just call this R, because it is well, we'll see later, it actually is a radius, but it is the hypotenuse. So we need to figure out what that value of R is to start out with. So that means that I have to square both of these sides, because both of these are the legs, because that's the right triangle. So I square these, add them up, and that's going to give me R squared. So this gives me, let's see, if I square the square root of 5, I get 5. Plus 36 is equal to R squared. So 41 is R squared, which means that R is the square root of 41. Okay, so we have R now. So now I can just write it in. Right? And then I'm going to go ahead and get rid of the Pythagorean computation here. Now we need to go through and figure out all of our trig functions. So let's start with sine, cosine, and tangent. Sine beta is going to be the opposite over the hypotenuse, which is square root of 5 over square root of 41. And we do need to rationalize the denominator here. So times square root of 41 times square root of 41. And that will give me, let's see, and you can always do this in your calculator or what have you. 5 times 41 should be 205. And 5 times 41 is its prime factorization. That's actually a good thing to note. 41's prime, 5 is prime. That's your prime factorization. That'll help you know if you can reduce anything. And then square root of 41 times square root of 41 is just 41. And if you did a factor tree on 205 to see if it's simplified, the only branches would be 5 and 41. There's no pairs in there. And there's nothing to cancel out with the 41. So that is the sine of beta. Then there's cosine beta, which would be the adjacent over the hypotenuse, which would be 6 over the square root of 41. And some of these will start getting quick for you because you can kind of see what's going to happen. If I multiply top and bottom by 41, I get 6 root 41 over 41. Right? So that actually went fairly quickly. And then tangent beta is the opposite over the adjacent, so that's just root 5 over 6. Right? So we have 3 function values here now. I have this one, and this one. And what we need to do is find the reciprocals to get the other 3. So the reciprocal of sine is cosecant. So cosecant beta is going to be root 41 over root 5. And if we rationalize that, I get the square root of 205 over 5. Secant beta is the reciprocal of cosine. And so that just ends up being the square root of 41 over 6. I'm going to put little stars by these things so we don't lose them. And then cotangent is going to be the reciprocal of tangent. So that's going to be 6 over root 5. And if we rationalize the denominator, that's 6 root 5 over 5. Right? And so those are our 6 trig functions. So hopefully you found those. Now, these are exact values. If you find the angle somehow and start plugging these things into a calculator, it's going to give you a decimal approximation. So plugging those answers in are actually not going to be valid answers in your homework. You need to have the exact answers involved in the root unless it tells you to round to a particular decimal place. Okay. So let's go ahead and clear this out, and we'll move on from there. Okay, so one of the last things I want to talk about today are special triangles. There's actually 2 of them. One of them is an isosceles. Let's try this again. Okay, there we go. One of them is an isosceles right triangle. So it's a right triangle, and remember, isosceles means 2 sides are the same. Exactly 2 sides are the same. So this side's the same as this side, and I have a right angle here. Despite what my drawing looks like, it's a right angle. What that does, since this is isosceles, that means the base angles are the same. So that means since everything has to add up to 180, these 2 angles are the same and they add up to 90. So that means each of them is 45 degrees. Right? And it's kind of interesting. When you take this 45 degree angle, let's go ahead and give these sides some length. Since they have to be the same length, I'm just going to call both of their lengths 1. And because of the fact that trig functions are true despite the size of the triangle, right? That's one of the powers of trig functions, is that they're true. Even if you take a triangle, one of these, a 45, 45, 90 with side lengths 1, and you blow the thing up, so it's still a 45, 45, 90, but the side lengths are like 100 or something. you still get the same side ratios. So all the trig functions still remain true regardless of the size of the triangle. If I use the Pythagorean theorem here, that makes my opposite side, my hypotenuse, the square root of 2. And so for 45 degrees, we can actually find all of the trig functions relatively easy because, and I always hesitate to use the word easy because that depends on your reference point. But if you memorize this triangle, you will know all 6 trig functions for 45 degrees, right? And that doesn't sound like much. What's that? That's one angle. Well, the angle shows up quite often, actually. This is one of the more common angles. And the other one that shows up a lot is something called a 30, 60, 90 triangle, which is 30 degrees, 60 degrees, and 90 degrees. Well, I'll just draw this, right? So this is my 30, 60, 90. Now, the other way you want to think about this is in terms of radians for the side lengths. 30 degrees, if you run it through the conversion, is pi over 6. 60 degrees is pi over 3. 90 degrees, just for reference, is pi over 2. 45 degrees is pi over 4. So both of these are pi over 4. So we're actually, later on as the semester progresses, we're going to be using these in terms of radians more than we're going to use these in terms of degrees. Just because radians has a much nicer, you can just do a lot more things with radians than you can with degrees. Okay, so now the other thing we need for this 30, 60, 90 are the side ratios. So the side ratios are 1, square root of 3, and the hypotenuse is 2, right? So I always remember it this way. 2 is the biggest number in here. The hypotenuse is always the biggest number, right? So that has to be 2. The shortest side is always opposite the smallest angle. So the 1 has to be opposite the 30, and that leaves root 3 to be opposite 60, right? That's how I remember it. Now, just showing you why this triangle is important, why it pops up so often. If you take an equilateral triangle, one that has all 3 sides the same, right? All 3 sides are the same measure, and you cut it in half, right? Well, with the whole triangle, every angle is 60 degrees in an equilateral triangle. If I cut this in half, that makes this 30, this 60, and this 90. And so the 30, 60, 90 triangle actually comes out of cutting an equilateral triangle in half. Oh, this vocabulary. I just work here, man. Okay. So looking at this, we can actually compute a few things. So if I wanted to find out, sine of pi over 3 times cosine of pi over 4, right? Let's say I wanted to work that out. Well, let's see if we can find this. We have pi over 3 here. So sine of pi over 3 would be root 3 over 2. And cosine of pi over 4, let's see here. Pi over 4 is 45 degrees. Cosine would be the adjacent over the hypotenuse. So that's 1 over the square root of 2. And we need to rationalize the denominator on this second one here. So if I multiply top and bottom by root 2, that changes it to root 2 over 2. And now I can just multiply these. I get root 6 over 4, right? We multiply straight across. And that doesn't reduce. So sine pi over 3 times cosine pi over 4 is root 6 over 4, right? And so it's just a matter of getting used to some of this arithmetic. We actually are going to end up doing a lot of this kind of arithmetic later on in the semester as we go through different kinds of problems. We'll find we have products and quotients and sums of different trig functions, and we have to be able to manipulate them down into something that's a nice little package like this. Okay, so I want to give you guys one to work on. So let me go ahead and clear this off. And let's see if you can do this. Let's do 6 times tangent of pi over 4. We'll make this a good one. Plus sine pi over 3 secant pi over 6. Now, I would strongly recommend sketching out the triangles when you deal with this stuff. I have pi over 4, right? So if I do 1 root 2, right, and that's my pi over 4. Tangent of pi over 4 is going to be 1 over 1. So this thing is just 1. So this is 6 times 1 plus, let's see, sine pi over 3. Okay, so we need the other triangle here. Let's do this. That would be 1 root 3, 2. It's a really good idea to just re-sketch these each time you use them because it helps you remember. Even if you have it right there in front of you, you don't need to write it down to reference it. Just re-sketch it. In the long run, it's going to help you out a lot. And that would be pi over 6, pi over 3, and pi over 2. So let's see here. Sine of pi over 3 is the opposite over the hypotenuse. So that's root 3 over 2. And then secant is the reciprocal of cosine. Okay, so pi over 6. Cosine pi over 6 would be root 3 over 2, but we are doing secant, so that would be 2 over root 3. Right? And now we go to simplify this. Well, 6 times 1 is 6, so that's not a big deal. Over here, I don't even have to rationalize the denominator. If I just multiply this straight across, I can cross cancel here, and this whole thing turns into 1. So this is 6 plus 1. The answer is 7. Right? Came out kind of nice. In fact, that simplifies more than they usually do. All right. I forgot to tell you guys to pause it. You should have paused it if you didn't. We'll try one more. Let's go ahead and get rid of this. And let's go ahead and do one more. So let's say we have sine of pi over 4 times cosine pi over 3 tangent pi over 3 times cotangent pi over 6. Let's have fun. Okay, so go ahead and pause it here. See if you can simplify this down. We'll see what happens. Okay, so let's go ahead and draw out our triangles. So first of all, we have our 45, 45, 90, right? So that's our pi over 4. And then the other one we have is our 30, 60, 90. So that's pi over 6, pi over 3, pi over 2, and that's 1 root 3 over 2. It's nice because of the fact that it works on any size triangle. You only have to remember one of them to remember all the ratios, which is convenient. Okay, so we have all that. Now it's just a matter of figuring out what the values are. So sine pi over 4 is going to be the opposite over the hypotenuse. So that's 1 over root 2. Cosine pi over 3, let's see, pi over 3 is up here, and it's the adjacent over the hypotenuse, so that's 1/2. Right, so that's those two. And then that's plus tangent pi over 3. So that's the opposite over the adjacent, so that would be root 3 over 1, which is just root 3. And then cotangent pi over 6, which is the adjacent over the hypotenuse, which is also root 3. So now it's just a matter of simplifying this down. And this one's going to have radicals in your answer. which is far more common than coming out with a whole number. Okay, so here we need to go ahead and rationalize the denominator here. So this ends up being root 2 over 2 times 1/2, which is root 2 over 4. So that's this first part. And then over here, root 3 times root 3 is just 3. So this is root 2 over 4 plus 3. Things to watch out for. Make sure you don't extend this square root down to the 4. That square root is entirely contained in the numerator of this fraction. That's a real common thing to do. It's easy just with bad handwriting. If you just, oh, that's really bad handwriting. Okay, let's try that again. Right? Some people do this, and you can't really tell that where the root stops, and then later on your eye picks it up, and then you continue the root through the whole fraction. You got to be careful of that. So make sure your handwriting, make sure what you write down is clear to you as well as another reader. In fact, a good way to do it is just imagine you're writing it down so you're explaining it to someone else. It's actually pretty difficult. So, all right. So let's see here. Okay. Oops. Oh, that's what I wanted. There we go. Okay. Now, I just want to end this with a little bit of foreshadowing to where we're going. We are kind of handling the material a little bit out of the order that the book gives it to you in. It just makes more sense to go in this order to me, so that makes it easier to explain. But where we're going here is this idea of the unit circle, right? If I take a circle, that might be one of the better circles. Someone screenshot that because I'm not probably going to do that anytime soon again. That's a pretty good circle. I'm kind of impressed when I like show somebody that. Okay. Anyways, if I take a circle like this, one of the things that we'll notice is that if it has a radius of 1, right? And I go ahead and look at the x and y coordinates of this point. Okay, so that point on the circle, this has a radius of 1, this has an x and y coordinate here. The equation of the circle with a radius of 1 centered at the origin is x squared plus y squared equals 1. And we are going to explain all this stuff again. What's interesting about this is if you look at this angle theta here, you can see the right triangle. And what's interesting, this right here, this height is your y coordinate. This distance across horizontally is your x coordinate. And what ends up happening is if you look at cosine theta right here, which is the adjacent over the hypotenuse, that's equal to x over 1, which is just x, which means my x coordinate here is actually cosine. And then sine theta is the opposite over the hypotenuse, which is y over 1, which is just y. And so those two, and this is part of the reason sine and cosine are the most important here, these two functions describe all the points on this circle all the way around. Right? And so if you can manipulate this, you can find these side lengths from this angle. Right? It ends up being a pretty useful thing. So, in any case, there we go. I want to go ahead and end here. This is where we're going. What this will allow us to do is plug in any angle, positive angles, negative angles, angles that are bigger than 180 degrees, right? Because you can picture an angle that goes down to here, right? And if you want sine and cosine of that, you can't draw the triangle, because how do you draw a triangle with an angle bigger than 180 degrees? But you can do it on the unit circle. So that's what we're heading to. This will allow us to connect all angles with a side length, right? With their side lengths. So, nonetheless, let's see here. We're at the end of our video, so I'll go ahead and wish you luck with this. Make sure you come and talk to me if you have any issues, and I will see you guys later. Keep your pencils and your wits sharp.